Hi, welcome to your third laboratory practice, Measuring Instruments and Balanced Three-Phase Systems. You may have consulted doctors from your childhood, and definitely you may have seen the stethoscope which doctors use to check the pulse rate. As same, electrical engineers also have an equipment like doctor's stethoscope. We call it as oscilloscope or oscope. So what is this so-called oscilloscope? Oscilloscope is an instrument that graphically displays electrical signals and shows how those signals change over time. Simply speaking, we can measure voltages and currents using an oscilloscope. So the multimeter also does the same thing, doesn't it? Why do we want an oscilloscope? Yes, multimeter can also measure the voltages, currents, frequencies, etc. But we can't visualize or display the voltage waveforms. Besides, we can't observe the instantaneous changes of a voltage or current signal over time using a multimeter or any other analog meters like moving coil, moving iron, or moving rectified meters. This is like the doctor can check the pulse rate with the aid of stethoscope. But if he wants to further investigate, such as the rhythm of the heartbeat, he should have an ECG report. As the same, we can just measure the voltages and currents using the digital multimeter. But if we want to observe how the voltages, currents change with time, we should have more advanced equipment like oscilloscope. So that is why we are using oscilloscope in designing, manufacturing, and in repairing an electrical equipment. Engineers use an oscilloscope to measure electrical phenomena and solve measurement challenges quickly and accurately to verify their designs. Before moving on identifying components of the oscilloscope, it is better to know about the history of the oscilloscope. In 1897, German physicist named Carl Ferdinand Braun invented the cathode ray tube, and along with it, the first oscilloscope, which was expanded upon decades later by the company A.C. Kosser. In 1934, the first commercial oscilloscope was released by General Radio, and it became the first to be used outside of a laboratory. In older CRT oscilloscope, the electrical signal under test changed the voltage between a set of vertical deflection plates that caused an electron beam to move up and down as it swept across a fluorescent screen. Modern oscilloscopes take measurements using an analog to digital converter to sample the signal and then draw the waveform on the screen. While all these buttons and knobs may seem daunting at first, but don't worry, let's identify the components of oscilloscope. First thing you can notice is the display. This is where the waveform and any information about it drawn. This port is used to connect a USB drive, and these two ports are used for calibration. Here we have two ports with colored bands that accept the probes with BNC connectors. We commonly see oscilloscopes with 1, 2 or 4 channels. In this oscilloscope, we have 2 channels. The vertical section controls the voltage scale on the display for each channel independently. The horizontal section controls the time scale on the screen for both channels. We can manually adjust how the oscilloscope triggers with this section, which tells the oscilloscope to start measuring when it sees a particular part of a signal. Menu section contains various settings, some of which we will use later. You will also be pressing single run stop quite often to start and stop measuring. As it turns out, scope probes are more than just some pieces of wire. The most common probes you will find are passive voltage probes, which mean that they measure the voltage differences between the round lip and this retractable hook tip. The hook is covered with a cover. To connect the probe, we have a special connector called BNC connector. And there you find the capacitor compensation trimmer. You can find the need of that later when we go to the practical. There are no active electronics in the probe, just some cable, resistors, and capacitors. If you want to look inside of the oscilloscope, you would find that each of the input ports has a 1 μΩ resistor and 16 picofarad capacitor connected in parallel to form the signal input to ground. Just connecting wires to the port would work for low frequencies, but since they look like antennas, they are liable to pick up noise and inject it into our circuit or measurement. To fix that, we use a flat shield cable to provide extra shielding. If you look at most oscilloscope probes, you will see a little switch labeled 1Hz on one side and 10Hz on other side. This refers the amount of the probe attenuates, that means reduces the amplitude of the signal. If you switch it to 1Hz, it is exactly like our robin. The tip is connected directly to the inner wire of the quartz cable of the probe, and the round lip is connected to the shielding. This works well for signals with frequencies less than few MHz. Quartz cable can act like a capacitor and add more than 100 picofarad to the test circuit. This can adversely affect many circuits, especially if you are trying to capture higher frequencies. As the remedy for this, many probes have option to enabling an inline 9 μΩ resistance to isolate the circuit for the cable. This is what 10H setting of the probe does. The 9 μΩ resistor in the probe and 1 μΩ resistor in the scope act as a 10:1 voltage divider. It is important to know that 10H does not mean 10 times gain. It means the signal is reduced by a factor of 10. The problem with adding a resistor in line with our signal is that with the capacitance, the quartz and oscilloscope, it creates a low-pass filter and high-frequency signals will appear smaller. You could learn much more about these filters in semester 4 under the circuit theory module if you were selected to electrical engineering field. To fix this, 10H probe include a variable capacitor in parallel with a 9 μΩ resistor. This is used to compensate for low-pass filter. This will keep the signal attenuation more or less the same across all frequencies. Now, I recommend leaving the probe on 10H, as that is the best compromise between signal attenuation and having the probe affect the circuit you are trying to measure. However, we need to inform oscilloscope that we are using a 10H probe and we need to tune the compensation capacitor in the probe. You will see the use of compensation capacitor later. Stay tuned. Let's connect the probe. Let's see how to calibrate the oscilloscope. First turn on oscilloscope and let it load. You'll likely only need to tune your probe once, but it's a good idea to check them every now and then to make sure that the compensation capacitor didn't get adjusted. We need to make some initial changes to the settings. First turn on channel 1 to see the input settings and make sure channel 2 is off. Ensure you are on DC coupling as we want to see all parts of our signal. Press the button next to probe. Highlight 10H using top left knob and press the knob to select it. Press the trigger menu button. Make sure type is set to H and source is channel 1. Most oscilloscopes come with some kind of built-in frequency generator, so we can test our probes and tune the compensation capacitor. This one happens to have a 1 kHz square wave generator we can use. Attach the round lip to the round tab and hook the probe around the signal tab. You should see something appear on the oscilloscope's display. Now we need to adjust the horizontal and vertical scale knob so we can clearly see the waveform. Note that turning the knobs clockwise decreases the time or voltage scale, which has the effect of zooming in the waveform. If you want to move the waveform up or down, you can adjust the smaller knob above the channel 1 button. Just note that this moves the 0 volt level for channel 1 as well. If the waveform seems to be moving or jittering, this is because the oscilloscope has no idea when on the waveform to start measuring, but we can fix that by adjusting the trigger level. Use the knob in the trigger section to raise the level of somewhere between the min and max of the waveform. This tells the oscilloscope to begin measuring as soon as it sees a rising edge, performs one sweep on the screen to draw the waveform, and then repeat the process. Now, these highs and lows should be completely flat, as we assume the oscilloscope is outputting a near perfect square wave. If not, it is because the compensation capacity in the probe has been tuned. So we are actually measuring the signal incorrectly. Using a tiny flat screwdriver, adjust the screw head in the probe until the square wave has straight edges. Note that some probes have the compensation adjustment through near the probes plugged instead. Now we have everything set up to take a voltage measurement. The oscilloscope is now ready to take measurement. Let's look at the circuit given in the lab sheet. Here are the AC supply, rheostat, and capacitor. Before constructing this circuit, we need to identify the apparatus in the laboratory. This is a variac, which is a variable AC power supply that provides AC voltage as output. Variac input is connected to 230 volts AC power supply. Variac output is connected to the circuit. You can see the rheostat, an electrical instrument used to control a current by varying the resistance. This is the capacitor. Here we have constructed the circuit. Variac output is connected in series with rheostat and capacitor as shown in the circuit. Channel 1 is connected to one terminal of the variac, while channel 2 is connected to rheostat. The point of which is common to both variac and rheostat is connected to one round clip. You can see small wires are connected like this to smooth the probe hook and round clip connections. Let's see how to connect probe hook and clip to the circuit. Here we have channel 1 and channel 2. Note that we must calibrate the second probe as the same way we calibrate the first probe. First state channel 1 probe. It is connected to one end of the variac output. The round clip is connected to the other end of the variac output. This will be our common point. Then, hook clip of channel 2 probe is connected to the rheostat terminal. Note that this round clip should be kept open to prevent short circuiting of the oscilloscope internal circuit. Now we have completed the circuit connected with probes. Then we need to apply 25 volt supply voltage using the variac output. Rotate the variac dial slowly in clockwise until oscilloscope RMS value shows 25 volts. After applying the voltage, we have to adjust the voltage and time sensitivity knobs so that waveform can be clearly observed. It is recommended to keep the voltage sensitivity as 10 volts per division and time sensitivity at 5 milliseconds per division. This means a small square will represent 10 volts vertically and 5 milliseconds horizontally. Note that one square is divided into 5 smaller divisions horizontally and vertically. Now adjust the vertical and horizontal knobs to place the waveform in the center of X and Y axis. This will be the voltage waveform of the power supply of the circuit. Sketch the waveform in the space provided in part 1 of the observations of your lab sheet. Now, we need to capture the voltage waveform across the rheostat. Switch off channel 1 and switch on channel 2. Keep the voltage and time sensitivity values as same as previous step. Then, turn on channel 1. Notice the phase shift between two waveforms. Change the resistance so that you can sketch the phase shift clearly and easily. Sketch the waveform in the same grid with supply voltage. Name the axis and waveforms clearly. Count the difference between two waveforms using smaller divisions. Use this information to calculate the phase shift. Let's see how to take a screenshot of the waveforms. Here is the USB port of the oscilloscope. Connect your USB drive. Press the print button. You can see the screenshot is saving. Once it is finished, you can remove the USB drive. For current measuring, we use a different probe called current probe. The operation of current probe is similar to a current transformer. It steps down the current, converts it to a voltage signal, and renders it to the oscilloscope. You can learn much more about current transformers in your upcoming semesters. Let's identify the parts of current probe. First, you can see the sensor head. The conductor goes through this sensor head. It can be opened using the opening lever. The current probe is powered through the power supply cable. We use BNC connector as the voltage probe to connect current probe to oscilloscope. These few parts are sufficient for you to know at this level, but if you are interested, you are most welcome to search. Now you are familiar with how to measure a voltage waveform. Let's measure a current waveform. You are already aware about the current probe. Let's see how each part connected to the oscilloscope. Here we are using a 4-channel oscilloscope. First, connect the BNC connector to one of the oscilloscope channels. Then, this power supply cable should be connected into the power supply ports in rear side of the oscilloscope. Now we are ready to take the waveform. We will be using the same circuit as previous. This is how we connect our sensor head. Then turn on channel 1. You can automatically see the current waveform here. Use this knob in vertical section to adjust current sensitivity, and use this knob in horizontal section to adjust time sensitivity. Here, observe the current sensitivity and time sensitivity. Sketch the current waveform in part 2 of the observations. At the end of first part of the lab practice, you learned what oscilloscope is, and then the parts of oscilloscope with probes and how to operate it, then how to calibrate the oscilloscope, and finally how to observe the waveforms. In the next part, we will deal with 3-phase circuits. So stay tuned. Welcome to the second part of Measuring Instruments and Balanced Three-Phase Systems Laboratory Practice. In this part, we are going to learn and observe the balanced three-phase systems. You may have seen the power transmission lines as well as the power distribution lines. There you can see 3 conductors and sometimes 4 conductors. This means the power transmission is carried out by 3 phases, 1 phase to each conductor. We call this as 3-phase power transmission. In these phases, each phase has a phase shift of 120 degrees to each other. So, what is this 4th conductor? It is the neutral conductor. Why do we use 3-phase power instead of single phase? There are a number of advantages of having 3-phase over single phase. We can reduce the current carrying capacity of conductors and we can reduce the cable size. On the other hand, in power generation, we use synchronous generators which are associated with 3-phase power. You could see these from your own eyes when you go for industrial training if you were selected to electrical engineering field. Besides, the industrial applications like high power machines, induction motors, welding equipment are working for 3-phase supplies. So, I encourage you to find out more about 3-phase power and its advantages. You will find it very interesting and enthusiastic. In 3-phase circuits, we have 2 basic configurations. They are star connections and delta connections. The source and load can be either in star configuration or delta configuration or mix of 2 configurations. Usually, the phases of 3-phase system is denoted by 3 colors: red, yellow and blue. In 3-phase circuits, it is always encouraged to have a balanced 3-phase circuit. Otherwise, there will be a number of issues we have to address. Balanced 3-phase circuit means while keeping the 120 degrees phase shift, we have to keep the magnitude and frequency of the sinusoidal voltage or current of each phase same. This means the vector addition of the voltages and currents of all phases should be equal to 0. In delta connection, phase 1 current plus, phase 2 current plus, phase 3 current should be equal to 0. If the system is balanced, that means if loads of all phases are same and supply voltages are same in magnitude and frequency with 120 degrees phase shift, then all currents are equal in magnitude and frequency with 120 degrees phase shift. If you observe the delta connection, the phase voltage and line-to-line voltage are same. Besides, the line current is equal to √3 times of phase current. In star connection, we have another conductor, which is the neutral conductor. So phase 1 current plus, phase 2 current plus, phase 3 current plus, neutral current should be equal to 0. If the system is balanced, then phase currents are equal in magnitude and frequency with 120 degrees phase shift. Therefore, neutral current will be 0. Line current and phase current are same, but line-to-line voltage is equal to √3 times of phase voltage. You may have learned these stuffs in your lectures and you know these equations well. In this part, we have a star source, star load configured circuit with a neutral current. There we are going to measure the voltages and currents of each phase using voltmeters and ammeters. Apart from that, we are measuring the line-to-line voltage and the neutral current as well. In each phase, we are measuring the power using 3 wattmeter method. There are some other methods to measure the 3-phase power. You would learn much more about these in upcoming semesters. When we use the wattmeter, we have sort of different connections than other meters. In the wattmeter, you have a current coil and a voltage coil. These 2 coils should be connected from one terminal. We refer it as common point. Here, A and C are connected and made them common. And then, current coil AB1 or AB2 is connected in series and voltage coil CD1 or CD2 is connected in parallel. You then think about it and understand. After taking these measurements, we are going to calculate the power factor. You then find it in your lab sheet. It is described with equations clearly. What will happen if the three-phase system gets unbalanced? We are going to see it practically as the second part of the practical. There, we change the load in one phase and observe the currents. You will see the current imbalance is mitigated by the neutral conductor. You will see not only the measurements but also the waveforms of currents with the aid of the oscilloscope. That is why we went through learning the oscilloscope. Now, let's move on to the practical. First, let's take a balanced three-phase system. You can see the circuit in figure 6 in your lab sheet, which consists of resistive and inductive load. 4 ammeters are connected in series with each phase and neutral wire to measure the RMS current. 3 voltmeters are connected in between each phase and neutral wire. 4th voltmeter is connected in between 2 phases to measure line-to-line voltage. Current coils of voltmeters are connected in series with 3 phases, while voltage coils are connected in between phase and neutral. This is the circuit built in the laboratory. Let's understand the circuit step by step. First, the resistive load. In given circuit, we use a 670 ohms resistive load. In the laboratory, we use 2 rheostats of 180 ohms and 490 ohms in series to get this load. See the series connection more closely. This is the inductive load commonly used in the laboratory. Then the star connection and the neutral wire. This point of 180 ohms rheostats of phase R, phase Y and phase P are used to form the star connection. Phases B and Y, phases Y and R are connected in one terminal, which is the common point of star connection. This common point is connected to one terminal of ammeter. The other terminal is going to the neutral point of the panel board. Let's see how 3 phases are connected. In phase R, from the 2 rheostats connected in series, the conductor or wire goes to one terminal of the inductor. The other terminal is connected to the ammeter. Ammeter is connected in series with the current coil of the voltmeter and finally connected to the phase R terminal of panel board. Phase Y is also connected in same manner. Rheostats, inductor and then ammeter are connected in series and finally to voltmeter current coil. From voltmeter, it is connected to phase Y terminal in panel board. Phase P connections are similar to phase R and Y. First rheostats, then inductor, then ammeter, then voltmeter, and then supply terminal in panel board. To be familiar with the laboratory equipment, have a close look at the terminal connections. See the voltmeter connections. Then ammeter connections and inductor connections. Now the line-to-line voltage. This voltmeter measures line-to-line voltage. It is connected in between phase Y and phase P. So it measures the line-to-line voltage of phase P and phase Y. Let's observe the voltmeter connections. Here, one terminal of all voltmeters is connected to neutral point. So phase B is connected to phase Y and phase Y is connected to phase R. So we formed a common point at phase R terminal. Then phase R terminal is connected to the neutral point. Now, we can measure phase R, phase Y and phase B voltages. Voltmeter voltage coil connections. As explained in voltmeters, voltage coils of voltmeters also need a common point. 240 volts voltmeter terminal of phase B, phase Y and phase R are connected together to form the common point, and then common point is connected to the neutral using a connector. To have a better understanding of the terminal connections, let's observe this connection diagram. Here we have same arrangement of what we observed in previous actual circuit. As we observed in that actual circuit, phase B resistor is connected to phase Y resistor, and phase Y resistor is connected to phase R resistor. Hence, we have formed the common point of star connection. Neutral conductor is connected to this common point. This neutral conductor is then connected to the ammeter, and through ammeter it goes to neutral point of the panel board. Then let's state phase R. In phase R, one terminal of resistor is connected to the common point and the other point is connected to the inductor. From inductor, the phase R conductor goes to I1 ammeter, which measures phase R current, and then the other terminal of I1 ammeter is connected to the current coil of voltmeter, and then the other terminal of current coil is connected to the phase R point of panel board. Same thing we can see in phase B as well. First we have the rheostat and then the inductor, and it goes to the ammeter, and from ammeter it goes to the voltmeter current coil, and then it is connected to the phase B point of panel board. Same thing happens in phase Y as well. In phase Y, first again the rheostat and then the inductor, and it goes to the ammeter, and from ammeter it goes to the voltmeter, and from voltmeter it goes to the phase Y point of panel board. Then we have to measure the line-to-line voltage. So we have chosen two phases, phase B and phase Y. So this voltmeter measures the line-to-line voltage. So one terminal of this voltmeter is connected to phase Y and the other terminal is connected to phase B. Then we have to measure the voltage of each phase. So in phase B, this voltmeter, this terminal is connected to phase B, and in Y phase, this terminal is connected to phase Y, and in phase R, this terminal is connected to phase R. So in each and every voltmeter, one terminal is connected to its relevant phase. So the other terminal is common. You can see VB3 terminal is connected to VB2, and that terminal of VB2 is connected to VB1. The same thing you observed in actual circuit. Now we have formed the common point. This common point is connected to the neutral conductor. In voltmeters, we use each and every voltmeter to measure the power of each phase. So we saw the current coil connections of each voltmeter, and now we are going to see the connections of voltage coil of voltmeters. So here you can see the voltage coil. So one terminal of voltage coil is connected to the common point of voltmeter, and it is connected to phase B. Here also the same arrangement. And then the other point. In phase B, the other terminal of voltage coil is connected to the voltage coil of phase Y, and that terminal is connected to phase R. So here also we have a common point. So this common point connects to the neutral conductor again. For this purpose, we have used a connector. Now all the connections are clear. So we are ready to take measurements and to observe the waveforms of currents of each and every phase and the neutral current using oscilloscope. When you are taking down the meter readings, Use the table in part 2.1 in the observations and fill it. Now turn on the circuit breaker and power up the circuit. Take the phase voltages and line-to-line voltage readings. Note that you must have a basic idea about the values of measuring voltages in order to select the proper range. After selecting correct range, you then read the voltage values. You then determine the proper range using connection diagram explained previously. Also take phase currents and neutral current readings. Write down the current values in observation sheet. Read the phasor power. Note the multiplying factors and terminal values of the wattmeter. You then refer the connection diagram to identify correct terminals. Now read phase Y power. Write down the power reading. Then read phase B power and write down the power reading. Let's see the waveforms of balanced system. First, phase R and neutral. Connect the channel 2 current probe and connect it around phase R conductor. You then see the waveform. Connect channel 1 probe around neutral conductor and observe the waveforms. You then see small ripples because of the harmonics in power supply. You then neglect them. Draw both waveforms in 2A grid provided in observation. Let's see phase R and B current waveforms. Channel 1 is connected to phase R and channel 2 is connected to phase B. Observe the two waveforms and sketch them in 2B grid in observations. Then phase B and phase Y current waveforms. Channel 1 is connected to phase B and channel 2 is connected to phase Y. Observe the two waveforms and sketch them in 2C grid. Then phase Y and R current waveforms. Channel 1 is to phase Y and channel 2 is to phase R. Observe the waveforms and sketch them in 2D grid. Then sketch all the waveforms in 2E grid. Let's learn about an unbalanced three-phase system. First, turn on the circuit breaker. Then notice the initial positions of rheostats. The system is balanced, hence the neutral current is 0. Phase currents are as previous. Probes are connected around neutral and phase R. Observe the waveforms of neutral and phase R respectively. Now let's make an imbalance in three-phase system by decreasing the resistance of one phase. Let's unbalance into 3 steps. First, decrease the resistance. Observe the neutral current reading and phase current reading. Notice the change in neutral current waveform. Decrease the resistance more. Observe the neutral current reading and phase current reading. Notice the change in neutral current waveform. Decrease the resistance further. Observe the neutral current reading and phase current reading. Monitor the change in neutral current waveform. Here you can observe the neutral current waveform changes gradually when resistance is decreasing. Draw the neutral current waveforms in each step on part 3 of observations. Observe the phase currents and neutral current readings in each stage. Compare with balanced system. Fill the table in observation sheet with readings. Now, let's make the imbalance of three-phase system by increasing the resistance. First, notice the balanced three-phase system. Then start increasing the resistance. Observe the neutral current reading and phase current reading. Monitor the change in neutral current. Here you can observe the neutral current waveform changes gradually when resistance is increasing. Increment is done only for one step. You then take down readings from the meters shown in above step. Draw the neutral current waveform in this step on part 3. In calculations, by using the observations of the part 1, calculate the frequency of the voltage waveform, peak-to-peak voltage, and phase shift between the voltage across the resistor and supply voltage. As the second part of calculations, calculate the power factor using the wattmeter, voltmeter, and ammeter readings of balanced 3-phase circuit. Then take a graph paper and sketch the phase current waveforms for one cycle. Now take in at least 7 points, including zero crossing points and peak points per half cycle of each phase current waveform, and construct the neutral current waveform as the sum of phase currents. Then take another graph paper and repeat above steps for one of the unbalanced stages. When you sketch the waveforms, make sure to mark axis, scale, and name the each phase. You can mark the points as shown in this figure. Then, for discussion, you have some questions to be answered. You can use the references in answering these questions. Finally, as a summary, we learned about 3-phase systems, different configurations like delta and star. Then we constructed a balanced 3-phase circuit and we measured the voltage, current, and power. We observed the phase currents and neutral current. Finally, we made an imbalance in 3-phase system and observed the currents. We reckon that this laboratory practice induced an enthusiasm to learn more about 3-phase systems and made an interest for electrical engineering. So, thank you for watching. Hope to see you in 7th semester in Department of Electrical Engineering.